All right, let's give this a shot. This is another experiment, so I don't know if it's going to work. But we're going to talk about containers and the history of containers. So, uh, containerization or hypervisors or splitting your machine off is wrapped up in the whole development of computers, right? So, we start out with large computers that are purpose built basically to fire missiles, right? Bang, right? That's what they're for. Um, and then you can argue the very first computers were for cryptography, whatever. Those really didn't catch on, by the way. Yeah, they did that first, maybe. Hard to know, right? So you get something purpose built to fire missiles, and then IBM's been in the compute business, not what we would call computers, but mechanical computers for a long time, and they're like, oh, we're going to build these mainframes. They're going to be great. They're going to do more than just calculate accounting statistics, right? Um, or hopefully they're not statistics, but sometimes they are. We're going to allow it to calculate all kinds of things and do all kinds of other things. And so this idea of having one large computer and many terminals arises, right? Oh, okay, we've got one centralized computer. Everyone's got their own little terminal, right? And so they effectively on a mainframe have an isolated environment that looks like what we would call one of the types of virtualization or containerization. So we move away from that with home computers, obviously, right? You got one user doing one thing at a time, and they struggle with things like doing two things at a time, right? They struggle with that, which is fine. Like they're for playing games, and the games struggle because right. And then you get into sprites, you get into all this stuff. So where do containers come in? Well, look, eventually this mid-tier market, right? So it was mainframes, mini frames, and then home computers, right? And workstations are kind of fighting to become existent at some point. And so they come to be. And then it just turns out that what happens is chip technology, because of quote Moore's law, keeps developing and developing and developing. And then we get to the point where Sun decides to do RISC. Now, I don't like RISC. RISC is stupid. There's lots of it. Looked great on paper, great. It just in real life it performs terribly. Right? There's a big trade-off. So at the time that Sun is doing this, it's making the worst possible trade-off. So it's taking memory, which is the most expensive component in a computer back then, right? And it's increasing the need for it to run the same amount of software. Right, because that's what RISC does. There's more instructions. They take up more space in the binary, just flat out, right, to do the same operation. Because if you can send one little thing that does basically 5 or 6 operations, right, 5 or 6 RISC operations, or you send 5 or 6 little RISC operations, guess which is bigger, right? So it actually is a significant problem, as it turns out. It doesn't seem like it should be or whatever, but your optimizations are being made in the compiler and not in the microcode, right? And so what ends up happening is you have lots and lots and lots and lots and lots of little instructions, optimized or not, right? And so they're optimizing for processor execution and speed and things like that. They're not optimizing for space. If you were optimizing for space, you'd have microcode. So why is this significant? Well, guess what takes less die space? RISC processors. Right. So as your density is increasing, you're running out of things to put on it. And this is actually why Intel wins, even though Intel makes the worst processors of all time, still to this day, with a few exceptions, but largely they were always lowest on the totem pole, right? MIPS had them beat, MOSTEC had them beat, like everybody had them beat. AMD always had them beat with their own architecture. That should have been a hint that maybe they suck, but we're here now. We can't cry about that anymore, even though we did at the time. Boy, did we. Anyway, so you've got huge dies, and you ain't got nothing to do with them. And your Sun. So what do? You put more CPUs on. Well, now this creates a problem. What's the user going to do with more CPUs? Well, really the right thing to do is to split the processes up and give them their own CPU where you can. And so, it's not just multi-processor, right? Because sometimes you want separate users. And so containers is the solution to that, where you're cordoning off a space inside the CPU for this, right? And so that's where, containerization is born. Now, we can go back a little bit further and say, wait a minute, Mark, but this multi-user problem, as workstations get bigger, as densities get higher on chips, right? As things get faster, you can have a server-based system and then a bunch of workstations, right? Servers costing $35,000, right? And workstations are like $5K a piece back then, something in that range. And that's back when that was real money, not nowadays. Maybe buy you some groceries for a day or something. So that's multi-user, and those big boxes usually had multiple CPUs or multiple cores or whatever, right? Usually both, and lots of memory. And then your workstation was pretty beefy anyway. I mean, X Windows is pretty heavy use case, right? So you need ways to isolate user processes. And since every Unix machine looks the same, like, can't tell a server from a workstation in Unix land very easily because they're running the same OS. And the OS doesn't look any different because it gives you all the same features effectively. So you already have the multi-user problem, and that causes some processor contention. And the way they cordon that off is with home directories and, down the OS stack, right? At the user level, at the user interaction level. So there's a ring 0, right? There's a ring 1, there's a ring 2, there's a ring 3. You're down at ring 3 doing the thing, no problems, right? The kernel figures out which things to prioritize and how to do that, and right. But the problem you run into is, well, now you want an environment at the user level to be isolated. Well, now you get chroot, and chroot is amazing. And my buddy was actually the first to use it in an ISP back in the 90s. And so he was doing chroot virtualization, virtual machines, way back. I think the early 90s. And, unbelievably successful at that, right? And so what comes of that is this need to isolate things further, but at a different layer, not at the user layer. You want the kernel to be aware of how to manage these things. The kernel can't manage a chroot because a chroot is just a file system jail. So you need something like in the middle of a file system jail where you can manage things a little bit more granularly. Well, that's where containerization, really comes in. And that's how these things start to work. Now, at the same time, there's a need for virtual machines, right? So we're virtualizing different layers, different aspects of the computer architecture, the whole stack, if you will. Boy, I hate that word because we've ruined it, but there's no such thing as a full stack developer, guys. That's not going to happen. So there's this hypervisor concept, and there's 3 levels of hypervisor, right? There's like VMware ESX, right? So that's the hypervisor runs on the hardware directly. There's no intervening OS. There's a small kernel, and everything else is hypervisor. Okay. Then there's like VMware Workstation, right? Which is where you have the hypervisor running on a host OS. And there's nothing wrong with that. That's fine. And then there's this third layer, which is containers, right? And so containers is a piece of software that runs on your OS that allows you to cordon off the hardware in a different way, right? By carving up the resources of the OS, whereas hypervisors work directly at the silicon level. So it's totally different. Now, the problem is that Sun had already invented containers. I mean, the BSD guys are ahead of everything. They had it first, right? But Sun had invented these containers for Java. A Java virtual machine should be a hint, JVM, right? That's a container. That's what it is. It's a type of server virtualization or machine virtualization, which is why in the JVM, you have to configure how much memory, you have to configure where your storage is and what access you have to it and all that. And then that causes security problems because of course it does. And we're not out of that mess, right? Because when you don't teach software engineers how the underlying OS works, and I don't mean Windows, because Windows A doesn't actually work. It's a miracle it runs at all for more than 10 minutes. And sometimes it doesn't even do that. I mean, like how these things are operating down below, especially in Linux land, we'll call it, or Unix land is the more proper term. So when you sort of engage with that, you kind of realize, oh, if you just knew how this stuff worked, you could write much better software and never use containers, because your configuration, which is what you've abstracted out with a container, needs to be consistent across your app, because otherwise you have management problems with your application and security problems. That's why 10, 12 years ago, cybersecurity didn't exist, and now it does. And that containers also got big in that time. This is not a coincidence. This is a side effect. This is a trade-off. So I wanted to sort of give you an overview sense of where these things come from and why it's important that you kind of understand the different types of hypervisors, right? And the different types of virtualization and what the goal is. Because a lot of things can be done better with chroot, right? And containers are really good for testing, so that you have a clean test environment and you're not using your ugly dev environment for testing. But they're bad for development. They're actually very bad for development, because I know this is a meme. It works on my machine times 1,000, right? Oh, well, I'll just ship you my machine. That's what it becomes. But software engineers are horrible at systems engineering work, and they should be, right? So yeah, pay attention to these things. It makes a big difference. It'll make you a better engineer once you understand them.